Hi, everybody. Um, we are starting our new chapter. Notice that we are on chapter 9, which means we are going to skip chapter 8 for a little bit. It is over nuclear changes and like radioactivity and those kinds of things. So I want to get this one done first. I feel like it's a little bit more important. It's a little bit more general information in terms of chemistry. So if time allows, we'll come back to some of the chapters we've gone past. So anyway, this chapter specifically deals with solutions. And remember, a solution is a type of mixture. And we've discussed mixtures back in chapter 2, I believe. And remember, that is anything, a mixture is anything where you have two or more substances, so elements or compounds, that are that are physically put together, not chemically, and they're not necessarily measured. It's a changeable ratio is the way that I have it defined here on the slide, which typically means it's like trail mix. I just dump it in a bowl. So I physically just put them all together, but I don't do anything to change them chemically. So they retain their distinguishing characteristics. I don't measure necessarily, or I don't count. So every mixture is different. And a solution, it falls into that category, and we'll talk about it more in a minute, but a solution is a mixture, but typically it is one with a homogeneous appearance. So before we get to that, let me real quick talk about heterogeneous mixtures. And this is a mixture where you do not have a uniform appearance. So you can see, see the parts of the mixture. So again, trail mix is kind of the go-to example of a heterogeneous mixture, at least for me. Trail mix. And so I can look at what is in my hand, before I eat it, and pick out the parts that I want first. There's nothing that changes about those parts, whether they're separate or together. Okay, so now a little bit more on heterogeneous stuff. There are a couple of different types to talk about, and the first one are suspensions. And this is a heterogeneous mixture of a fluid. And remember, a fluid can be a liquid or a gas. We typically tend to think of it as just a liquid, but it can be a gas also. And there are large particles that will settle out over time. And so I've got some examples there. Aerosol spray, so like hairspray or something like that in the can, is a liquid suspended in a gas. And so it's like like if it's air freshener, and you spray it, it will disperse. It'll settle out eventually. Over time, though, those liquid particles will start to settle. And if you like sometimes, like if you sprayed it and then you can still, like, it lands on your hand, like it settles out. Airborne dust, this is a solid suspended in a gas. Sometimes you'll see this, like, in your house, if the sunshine is coming through the window at just the right angle, and you look from just the right angle, you can see kind of the sparkles of dust in the air. Eventually they settle. It seems like they don't, but eventually they will settle out. Mud is a solid suspended in a liquid, so it's just dirt particles in water. Oil and vinegar, salad dressings, a liquid suspended in a liquid. It stays suspended. Actually, in this one, the oil will, because the two don't mix because of their chemical properties. But you also have things like orange juice with pulp is a suspension, and so I typically get the non-pulp orange juice. But if you have pulp orange juice, you shake it up before you pour it, so that you don't, the last bit of the orange juice bottle is not just pulp. When you guys were little, you probably had medicines in liquid form, and they a lot of times just said oral suspension on them, and like your mom would have to shake it up before she gave it to you. And so so I'll get different kinds of that. Chocolate milk, I like to shake that up a little bit. It feels like it settles. But anyway, so those are all different examples of suspensions. Then we have colloids. Now, colloid is a heterogeneous mixture where the particles are too small to settle. But they're big compared to the next thing that we're going to talk about, which is a solution. And so the particles don't settle, they remain suspended because their size is fairly small, but also just because of Brownian motion and those kinds of things. So they just stay suspended, and they typically have a uniform appearance. So I can't see the things, because they are not settling, but I can determine or distinguish between a solution, which has even smaller particles, and then a colloid by what is called the Tyndall effect. And so this picture represents the Tyndall effect right there. And so the first glass, or the first whatever that is a solution. And notice how the laser just goes right through it. You can't see anything right in there. In the colloid, because the particles are big enough, they actually will reflect the light. And so that's why you can see like that little beam right in the middle. And so that's kind of the easiest way to distinguish between a colloid and a suspension. But some examples: whipped cream is considered a colloid. It's gas dispersed in liquid. Now, over time, of course, it will flatten because the gas will come out of the liquid just as the liquid is disturbed and the gas kind of rises. Mayonnaise is liquid oil of some sort dispersed in vinegar. Again, doesn't settle. It has a fairly, it's not quite a solid, but has a fairly firm texture to it. Paint, you have solid particles dispersed in liquids. So this is like, you do have to shake some paints, but most of them, the color will stay, or just some of the solids will settle. A marshmallow is a colloid. It's air dispersed in a solid, and that's what makes them kind of fluffy. Some other examples of colloids, those are like butter is considered a colloid, I believe. Milk might be considered a colloid. I'd have to look others up, but those are they all kind of seem foodish. But so yeah, so you do have particles in there, and you can't see them because of their size, but they're small enough, but also big enough that you can use that whole Tyndall effect. Okay, so now on to the homogeneous mixtures, which are solutions. So we've been kind of clarifying the difference between suspensions, colloids, solutions. A homogeneous mixture is a mixture where you have that uniform appearance. So I look at it, my eye can't distinguish any difference within that substance, but it still has that changeable ratio. So it's not, I don't have anything that is necessarily measured. It's all, kind of variable. The particles are smaller than colloid particles, so that's why the Tyndall effect doesn't work here. And they are typically uniformly distributed. So because of the Brownian motion and the way that the particles are kind of keeping each other separated, everything just stays dispersed. In a solution, you have two main parts, the solute and the solvent. The solute is the substance that dissolves. And typically, it's what you have a smaller amount of. The solvent is a substance that does the dissolving. So it's the substance into which the solute dissolves, and you usually have the larger amount of this. So that's just, if you have like two of the same states of matter and you're dissolving them together, like alcohol into water, depending on which way it is working, if the alcohol is the lower amount that you're putting into water, the greater amount, it's the solute versus solvent. All right, so some examples that you're probably pretty familiar with: salt water is a liquid solution. It's liquid because the base, or the water, is liquid, but you put salt in as the solute and it dissolves into the water, which is the solvent. Air, so the stuff all around us, is a gas solution because the main component, nitrogen, is a gas, but you have various gases that act as the solute. Oxygen, of course, CO2 gas is in the air, water vapor is in the air, but the main component, so the solvent in this case, is nitrogen. And then you also have things like bronze, which is an alloy. So alloys are when typically it's two metals, but that bronze is an example of one. It's a solid solution. And so you have tin, which is the smaller amount, dissolved into copper, which acts as the solvent. So then some other examples of solutions, Kool-Aid, stainless steel is kind of like bronze, is the alloy. I'm sure there are others now, I just can't think of any of them, but you get the drift. Okay, so now forming solutions. So what does it take for a solution to form? The process is actually called solvation, and this is where a solute dissolves into a liquid solvent. It's pretty specific in that, and typically it involves the positive and negatives attracting each other between the different particles. So for example, if you have salt and you're dissolving it in water, the positive ends of the water are attracted to and pull on the negative chloride ions. And there's a picture on the next page. So if all this seems kind of crazy, there's going to be a visual here in a minute. But then the negative ends of water are attracted to, and then they pull on the positive sodium ions. And so remember, water's polar. And so remember, it has this shape to it. So you've got H2O. And remember, the O is the negative and the H's are the positive. So that's when I say, you know, the positive ends of water, that's, excuse me, oh, my nose is really itchy today. And then so the positive ends are by the hydrogen, the negative are by the oxygen. Anyway, the ions get pulled apart. The sodium gets pulled away from the chlorine and then becomes surrounded. And at that point, solvation has happened. Now, once, good grief, the individual ions, the sodium and the chlorine, are completely pulled apart, this is where you have actual dissociation. So everything has separated out. Okay, so let's look at this picture. Okay, so here we have the green and the blue are the sodium and the chloride. The chloride is green and the sodium is blue, just in case you're wondering on that. Oh, there's a key at the bottom. And then the kind of the red and the kind of little white circles on there, those are water molecules. And so with the water, the white parts are the positives. So here's the positives on that one. And then the negative is on the red end. And so notice on like this picture, you know, this part up here, you have the negative, and all of the whites are moving in to surround it. And so it is completely surrounded by positives because positive and negative attract. Same thing down here with this one. The positives in the middle and all the negatives are facing it. And so that's what ends up happening. And so these two, you know, this one and this one end up being pulled apart and are very far apart by the time dissociation happens, and they are dispersed equally, and so they stay dissolved, they stay kind of held up by the motion of that water. Okay, so now with solutions are some things that you can just kind of talk about. The first one is solubility, and solubility is basically how much will dissolve, the degree of dissolving. It's measured by what's the max amount that I can dissolve in this amount of water or this amount of solvent at a certain temperature. And so, you know, typically, you know, it's room temperature, or, you know, whatever it is. But this is the solubility curve, is that picture with the different lines on it. And so along the bottom is the temperature, along the side is how much can be dissolved in 100 grams of water. So there's the amount. And so notice that most of them, as temperature increases, most of them increase solubility, or they have the ability to have more dissolve. There are a few that either kind of just stay level, don't really change at all, and then also just a couple that decrease if you increase temperature. And so that's just kind of a way to check kind of how much will dissolve, that kind of thing. Solubility also depends on what is actually being dissolved, like what kind of substance is it. Typically they look at polar or non-polar, and the way that they kind of have termed it is that polar will always dissolve polar. It has to have, you know, a positive negative to be dissolved by a positive negative, and then non-polar dissolves non-polar. So if they don't have the positive negatives, they need, those two will work. And that one, a lot of times you'll hear them just refer to this as like dissolves like. They have to be alike both polar or both nonpolar, for them to mix together. Temperature also plays a role, which we've kind of already talked about. Pressure, if you're talking about dissolving a gas into a liquid, can determine solubility. Higher pressure typically results in more gas being dissolved. So that's why, like when you open a Coke bottle and it fizzes, that fizz is the actual pressure that's been put into that bottle to maintain the bubbles basically in that carbonated drink. Okay, so now rate of dissolving. Can I make something dissolve faster? Yes. And we've actually already talked about this when we talked a little bit about just chemical reactions, where there are three ways, or there were multiple ways that we talked about to make the reaction happen faster. And those go along with dissolving. You can heat it up to make the particles move faster. You can stir it up so that more particles will come in contact. And then you can crush it up to increase the surface area. And so remember, we used our example of making hot chocolate, and all those things apply. So it's again kind of a you do this part. You know how to do this. Okay, so now separating mixtures should be pretty easy because they are physical combinations. They can be separated by physical means. So it means I don't have to do any big things. I just kind of rely on their properties, but also on just some really easy techniques. So for example, evaporation can be used to remove a solid solute from a liquid solvent. So if I had a cup of salt water and I wanted to just get the salt, it would take a while. I could just let it set, and I could wait until all of the water evaporates and I would be left with salt. I could speed up the evaporation by boiling it and evaporating the water that way, but I would get the salt back. Those of you who are doing honors, that I think I'll have on the essay or the kind of little research talking about how they take salt out of water. People who live close to like the Dead Sea over in the Middle East, it's Dead Sea salt is a big product over there, and they basically can pick it up because it washes up on the shore, the water, and the water evaporates, as it kind of goes back, and they're left with all this salt. So they can use that and sell it. Magnetism, if I have something magnetic mixed with something that's not magnetic, then I can use a magnet to remove the magnetic stuff. Sifting, filtering, I can pour things basically through kind of like a filter and get larger particles out. And that could work with a liquid. That could work with two solids. If I had rocks and sand, I would just have to pour it through some kind of filter, and the sand would go through, but the rocks would stay. And then the last one, distillation. This removes a liquid with a low boiling point from a liquid with a high boiling point. So if I had a mixture of something like alcohol and water, and I wanted to remove the alcohol, it's going to boil at a much lower temperature than water. So, it kind of takes kind of an elaborate setup, but I could boil it, get rid of that, and then end up with pure water left over. And then some examples of mixtures, I've kind of mentioned some of them as I've gone through, but pretty much anything you can think of, you can fit it into those groups. Okay, so now solution concentration. So concentration is defined as the actual amount of solute dissolved in a given amount of the solution, total thing. And there's some words that we use. Concentrated means there's a large amount of solute. Diluted means there's a low amount of solute, kind of comparably. I think we'll do a lab problem in here, like where we make some Kool-Aid, and we'll talk about whether it's concentrated or dilute. Also, some terms to know are saturated. A saturated solution contains the maximum amount of solute that the solution can hold at that temperature. So it is just holding the right amount. If you put any more solute in, that solute will have to settle to the bottom because the solution just can't hold more. Unsaturated means you can put more in and it will dissolve pretty easily. Supersaturated is kind of a special case. It actually contains more solute than the solution should hold at that temperature. And these solutions have to be have to be made. Essentially, you heat it up to dissolve more, and then you can cool it back down. Syrups are supersaturated solutions, and then we have some like rock candy is a result of a supersaturated solution. You take water and you dissolve a whole bunch of sugar in that water as you heat it up, and then you allow it to, or you can cause it to crystallize, and it's what makes that cool rock candy. Okay, so here's kind of a little picture of that. So unsaturated, you kind of look kind of closely, but there aren't really any white dots. That means I can dissolve more. The saturated, I'm going to notice kind of the equal distribution of all the little white dots in there. Any more would have to settle to the bottom. Super saturated over here, it holds way more, and if I heat it up, I could get it to dissolve, and then it would all, and cool down, it would all have the an excessive amount compared to the saturated. Okay, so now some math, and we'll do these in class together, but there are two things to know. We're going to talk about percent by mass, which is the mass of the solute over the mass of the solution times 100. I've given you the examples from the chapter if you want to go back and look at those, but these are basically how to make a solution if I want a certain percent, and we'll do some different ones, but it gives you kind of gives you all this stuff, and it becomes an algebra problem where you just end up solving for x. And so we'll work this one out in class, although I highly encourage you to try it yourself. Same for this one, percent by volume. So now we're looking at volume of the solute and volume of the solution. So same thing as far as the example goes, you're going to solve for x, and we'll talk about how to set all that up in class. And then finally, just kind of a brief explanation of colligative properties. These are properties of solutions that change if you change the concentration of the solution. And there are actually three pretty common ones. I've got the two most common ones listed here. The first is boiling point elevation. So as I increase the amount of solute in a solution, so say I have pure water versus salt water. So I'm changing the amount of solute. I'm dumping more salt in and leaving some water pure. The boiling point will increase. So the solution of salt water in that example will boil at a higher temperature than a pure solvent. So if I have pure water and salt water and I put them on the stove at the same time and I have a a thermometer to measure, the pure water is going to boil at 100 degrees Celsius. The solution, depending on how much salt is in there, it might be more like 102 degrees. So it's not necessarily, this huge drastic change, but it's noticeable, and so it's a measurable thing, and it's based on that concentration. Freezing point depression, as the amount of solute increases in the solution compared to the pure. So again, if we did pure water versus salt water, the freezing point decreases. So the solution will freeze at a lower or a colder temperature than a pure solvent. So again, if I have pure water and salt water, and I stick them both in the freezer, and I keep going back to measure and kind of look at the temperature, water is going to freeze when it reaches 0 degrees Celsius. The salt water, depending again on how much salt is in there, it might need to be like -4 degrees, or whatever that is. And it's one of the reasons that we didn't, it's Oklahoma, so we don't have a lot of ice on the roads, but people used to put down salt. They would salt the roads. Mr. Fratsky does sometimes, like in our parking lot, he puts out those like blue crystals. That's a salt, basically. The salt won't allow the water to freeze until it gets even colder. And so unless the temperature gets really, really low, the salt will kind of keep the ice from forming and kind of keep everything from getting too icy. FYI, they don't typically put salt out on roads anymore because it rusted like the undercarriage of the cars, a long time ago. And so they stopped doing that, and and so it helped with car damage. They put sand down now. We do that here, you know, on the few occasions that we have ice. The sand is there more for the wheels to get traction. It doesn't really do anything to the ice because it doesn't mix well. So, but anyway, so that's that. We will go over it more in class. Please let me know if you have questions. All right, I can't turn it off.